Welcome to the e-lecture session for diploma students. In today's class we are going to see the condition for maximum efficiency in a transformer. When a transformer works on a constant input voltage and frequency, then the efficiency varies with the load. As load increases, the efficiency also increases. Now here you can see at a certain load current. So, up to this point the efficiency increases. Once it attains the maximum point at certain load current, after that again it tends to fall. As the load increases, the efficiency also increases. At a certain load current, it achieves a maximum value. If the transformer is loaded further after this particular point, if you continue to load the transformer, you can expect a slight dip in the curve. It is slightly drooping after this. So, at a certain load current, it achieves a maximum value. If the transformer is loaded further, the efficiency starts decreasing. The graph of efficiency against the load current I2 is shown in the figure 3.29. The load current at which the efficiency attains maximum value is denoted as I2 max, and the maximum efficiency is denoted as eta max. The efficiency is a function of load, that is the load current I2 assuming cos phi 2 as constant. The secondary terminal V2, the secondary terminal voltage V2 is also assumed constant. So, for maximum efficiency the condition is d eta divided by, that is rate of change of eta with respect to the current I2 should be equal to 0. We know that eta is equal to V2 I2 cos phi 2 divided by V2 I2 cos phi 2 plus iron loss, that is Pi, plus I2 square R02, that is total copper loss. Now, we need to find out the condition for the maximum efficiency. So, d eta divided by di2, the rate of change of the efficiency with respect to I2, which is equal to d by di2 V2 I2 cos phi 2 divided by V2 I2 cos phi 2 plus Pi plus I2 square R02 equal to 0. So, I am multiplying both the left hand side and right hand side expressions with this expression, that is V2 I2 cos phi 2 plus Pi plus I2 square R02. So, once you multiply this, you can get V2 I2 cos phi 2 plus Pi plus I2 square R02 d by di2 of V2 I2 cos phi 2 minus V2 I2 cos phi 2 d by di2 of V2 I2 cos phi 2 plus Pi plus I2 square R02 equal to 0. Now, this is a constant value. So, once you find out, once you differentiate this particular component, that is parameter expression V2 I2 cos phi 2 with respect to I2, you get V2 cos phi 2. Similarly, once you differentiate this, you get V2 I2 cos phi 2 is the expression already there into V2 cos phi 2 plus this I2 square is, once you differentiate this, it will become 2 I2. So, R02 is a constant into R02 is equal to 0. So, further simplifying all these expressions, you will get Pi is equal to I2 square R02. So, we know that this expression I2 square R02 is nothing but the copper loss and Pi is the iron loss. So, once you derive the condition to achieve the maximum efficiency in a transformer, finally you end up with the expression copper losses is equal to iron losses. So, this is the condition. Whenever you have iron loss is equal to copper loss, the efficiency, the corresponding efficiency of the transformer would be maximum. All day or energy efficiency. The primary, this is one kind of efficiency. The primary of distribution transformer is connected to the line for 24 hours a day. Thus, the core losses occur for the whole 24 hours, whereas the copper losses occur only when the transformer is on load. The distribution transformers operate well below the rated power output for most of the time. It is therefore necessary to design a distribution transformer for maximum efficiency occurring at the average output power. The performance of the distribution transformer is more appropriately represented by all day or energy efficiency. The energy efficiency of a transformer is defined as the ratio of total energy output for a certain period to the total energy input for the same period. The energy efficiency can be calculated for any specific period. When the energy efficiency is calculated for a day of 24 hours, it is called as the all day efficiency. The all day efficiency is defined as the ratio of energy output to the energy input taken over a period of 24 hours. So, the all day efficiency is given by energy output over 24 hours divided by energy input over 24 hours into 100. Then comes the polarity test. A polarity test is carried out to find out the terminals having the same instantaneous polarity, assuming that the terminals are not marked. Then parallel operation of single phase transformers. If the amount of power to be transferred is greater than the capacity of the existing transformer, it is necessary to connect two or more transformers in parallel. Now, we can derive the conditions for the parallel operation. For parallel operation of transformers, certain conditions have to be met. What are those conditions? These are the conditions. Number 1, the turns ratio and the voltage ratings of the transformers to be connected in parallel should be same. Number 2, the polarities of transformers should be same. Number 3, percentage impedance of the transformers should preferably be same. Number 4, ratio of resistance to reactance should be same. So, these are the few advantages of parallel operation. The total load of the circuit can be increased. If any one transformer fails to supply, the continuity of supply is maintained by the other healthy transformer. Number 3, maintenance of each transformer can be carried out without any interruption. So, here is a diagram showing the two single phase transformers which are connected in parallel. So, these two are the primary and these two are the secondaries. Those secondaries are so well connected to form a parallel combination of these two transformers. Then auto transformer, a transformer in which a part of the winding is common to both primary and secondary circuits is known as an auto transformer. The primary is electrically connected to the secondary as well as magnetically coupled to it. So, this is the schematic diagram of a auto transformer. The coil A B represents the primary winding, whereas the coil C B C represents the secondary winding. So, this is the applied voltage V1 given to the auto transformer. Here you can connect the load is connected to the secondary. So, the primary winding has N1 turns and the secondary winding has N2 turns. If no load current and iron losses are neglected, then I can say V2 by V1 is equal to N2 by N1, which is equal to the voltage transformation ratio. The current in the section BC is a vector difference of I2 and I1, but since the two currents are practically in phase opposition, the resultant I2 minus I1, where I2 is greater than I1. The current in section BC is a vector difference of I2 and I1. So, it is equal to I2 minus I1, where I2 is greater than I1. Saving of copper in comparison to conventional two winding transformer. The volume and hence the weight of copper is proportional to the length and area of cross section of the conductors, but the length of the conductor is proportional to the number of turns and cross section depends on current. Hence, the weight of the copper is proportional to the product of number of turns and the currents to be carried. So, the weight of copper in conventional two winding transformer is proportional to the ampere turns, that is N1 I1 plus N2 I2. Weight of copper in auto transformer is equal to weight of copper in section LS plus weight of copper in section MS. But the weight of copper in section LS is proportional to N1 difference N2 into I1. Weight of copper in section MS is proportional to N2 into I2 minus I1. So, the weight of copper in auto transformer is proportional to the addition of these two expressions, that is N1 minus N2 into I1 plus N2 into I2 minus I1. So, the weight of copper in auto transformer divided by weight of copper in ordinary transformer is equal to N1 minus N2 into I1 plus N2 into I2 minus I1 divided by N1 plus I1 N1 I1 plus N2 I2. So, upon simplification you get the expression like this. So, which is equal to 1 minus k. We know that N2 by N1 is equal to k, or I2 by I1 is equal to 1 by k. So, the saving in copper is equal to k into W naught. So, the saving in copper can be expressed as the voltage transformation ratio into the weight of copper in the ordinary transformer. So, it can be proved that the power transformed is equal to input into 1 minus k. The rest of the power is conducted directly from the source to the load. So, the advantages of auto transformers, here are the few advantages we can list out. One is saving in conductor materials, just now we have seen that, and the cost will be less because of that. The power loss is reduced, so the efficiency will be very high. Higher kVA rating. Number 4, lower percentage reactance, hence better voltage regulation. Number 5, can be used for obtaining variable voltage supply. Disadvantages: if there is a break in the secondary winding, full voltage flows from primary side to the secondary side. Number 2, auto transformer winding needs more insulation than that of a 2 winding transformer. Applications of auto transformer: it is used as a starter for a 3-phase induction motor. It is used in electrical furnace. Number 3, 3-phase auto transformers are used in the interconnection of grids. Number 4, to give smooth variation of voltage to test circuits in the laboratories and acts as a booster. Now, let us do some of the problems in the transformer sections. Number 1, a 40 kVA single phase transformer has 400 turns on the primary and 100 turns on the secondary. The primary is connected to 2000 volts 50 hertz supply. Now, determine number 1, the secondary voltage on open circuit. Number 2, the current flowing through the 2 windings on full load. Number 3, the maximum value of flux. First of all, we will write down the given data. The rated power is equal to 40 kVA. Number of primary turns N1 is given as 400. Number of secondary turns N2 is equal to 100. Then supply voltage V1 is equal to 2000 volts. Supply frequency is 50 hertz. We need to find out the secondary voltage on open circuit, current flowing through the 2 windings I1 and I2, maximum value of flux, that is phi max. The secondary voltage on open circuit is equal to E1 into N2 by N1, which is equal to 2000 into 100 divided by 400, which is equal to 500 volts. Then primary full load current is equal to rated power divided by V1. So, we know that the rated power is given as 40 kVA. So, 40 into 1000 volt ampere divided by V1 is 2000. So, the primary full load current is 20 amperes. Then secondary full load current I2 is equal to rated power divided by V2. Already we have found out the value of V2, which is 500. We can straight away substitute 40 kVA divided by 500. So, the secondary full load current magnitude will be 80 amperes. Then the maximum value of flux phi max. Using the EMF equation E1, which is equal to 4.44 F phi max N1. Phi max is equal to, you can segregate this phi max on the left hand side and the remaining parameters on the right hand side in the EMF equation to get E1 divided by 4.44 f n1. So, all these values E1 is known, frequency is known, and the number of turns in the primary is known. Substituting and upon simplifying, you get phi max, that is the magnetic flux, is equal to 0.0225 Weber. Now, let us move on to the second problem. The no load ratio required in a single phase 50 Hertz transformer is 6600 divided by 600 volts. If the maximum value of flux in the core is to be around 0.02 Weber, find the number of turns in each winding. Given data is equal to supply frequency 50 Hertz, primary voltage V1 is equal to 6600 volts, secondary voltage V2 is equal to 600 volts. Then we need to find out the number of primary turns and the number of secondary turns, and then the maximum value of flux. Using relation E1 is equal to 4.44 f phi max n1, we can straight away find out the number of turns n1, which is equal to E1 by 4.44 f phi max. All the other values parameters are available. So, E1 is equal to 6600, then frequency is 50, phi max is given as 0.08 Weber. So, by substituting and upon simplifying, you get the number of primary turns as 372. Then similarly, by applying the other EMF equation, E2 is equal to 4.44 f phi max n2, you can find out the number of secondary turns n2 as 34. Then we will move on to the 3-phase transformers. A 3-phase system is used to generate and transmit very large power. 3-phase transformers are required to step up or step down voltages in various stages of a power system network. Transformers for 3-phase circuits can be constructed in one of the following ways. Number 1, 3 separate single phase transformers are suitably connected for 3-phase operation. Such an arrangement is called a 3-phase bank of transformers. Or on the other hand, number 2, a single 3-phase transformer in which the cores and windings for all the 3 phases are combined in a single structure. The present day system is a 3-phase system. The change of voltage in a 3-phase system is performed either by a single 3-phase transformer or by a 3 single phase transformers. Then advantages of 3-phase unit transformer. A 3-phase unit transformer has the following advantages over 3 single phase transformer bank of the same kVA rating. Number 1, it takes less space, it is lighter, smaller and cheaper, it is slightly more efficient. A single unit 3-phase transformer has a 3-limbed core, 1 limb for each phase winding. On each limb, the low voltage winding is placed over the core and the high voltage winding is placed over the low voltage winding, with suitable insulation between the core and the low voltage winding as well as between the two windings. Figure 4.1 and 4.2 show the schematic diagrams of 3-phase core type and shell type transformers respectively. So, this is the core type transformer and this is the shell type transformer. 3-phase transformer connections. The primary and secondary winding of a 3-phase transformer can be connected in either a star mode or in a delta mode. Hence, 4 main connections are possible. One is star star, second one is star delta connection, and delta star and delta delta, finally open delta connection. Factors affecting the choice of connections. Some of the factors governing the choice of connections are as follows. Number 1, availability of a neutral connection for grounding, protection or load connections. Number 2, insulations to ground and voltage stress. Number 3, availability of a path for the flow of third harmonic currents and zero sequence currents. Number 4, need for partial capacity with one circuit out of service. Number 5, parallel operation with other transformers. Number 6, operation under fault conditions. Number 7, economic considerations. Now, we will discuss about the first topic, which is star star connection. You can see here, I can zoom this on. You can see here, this is the R phase, Y phase, B phase, and this is the neutral. There are two ends for a phase, right? The one end of R phase, one end of Y phase, and one end of B phase, all are interconnected to form a single point called as neutral. So, this is a star network. Similarly, here also one end of R phase, one end of Y phase, and one end of B phase are all interconnected, which is designated as a neutral signal. In this type of connection, both the primary and secondary windings are connected in star, as shown in the figure 4.4. This particular connection proves to be economical for small transformers, as phase voltage is 1 by root 3 times that of line voltage. The number of turns per phase and the quantity of insulation required is very minimum. The ratio of line voltages on the primary and secondary sides is same as that of the transformation ratio of each transformer. It can be noted that there is a phase voltage shift of 30 degrees between the phase voltages and the line voltages on both primary and secondary side. The line voltages on both sides and the primary voltages are in phase with each other. The connection of primary neutral to the neutral of generator has an added advantage that it eliminates the distortion in the secondary phase voltages. If the flux in the core has sinusoidal waveform, then it will give sinusoidal waveform for the voltage, but due to the characteristics of iron, a sinusoidal waveform of flux requires a third harmonic component in the exciting current. As the frequency of this component is thrice the frequency of the circuit at any given instant, it will try to flow either towards or away from the neutral point in the transformer windings. With isolated neutral, the triple frequency current cannot flow, so the flux in the core will not be a sine wave and the voltages are distorted. If primary neutral is connected to generator neutral, the triple frequency currents get the path to solve the difficulty. The alternative way of overcoming this difficulty is the use of tertiary winding of low kVA rating. These windings are connected in delta and provides a circuit in which triple frequency currents can flow. Thus, the sinusoidal voltage on primary will give sinusoidal voltage on secondary side. If VL1 is the line voltage on the primary side, then phase voltage on primary side is given as V phase 1 is equal to VL1 divided by root 3. So, here are the few advantages of a star star connection. Due to star connection, the phase voltage is 1 by root 3 times the line voltage, hence less number of turns are required. Also, the stress on the insulation is very less. This makes the connection more economical. Due to star connection, the phase current magnitude is same as that of the line current. Hence, the windings have to carry very high currents. This makes the cross section of the windings very high. Thus, the windings are mechanically strong and the windings can bear heavy loads and short circuit. There is no phase shift between the primary and secondary voltages. As neutral is available, it is suitable for a 3-phase 4-wire system also. So, here are the few disadvantages of star star connection. If the load on the secondary side is unbalanced, then the performance of this connection is not satisfactory. Then the shifting of neutral point is possible. To prevent this, star point of the primary is required to be connected to the star point of the generator. Even though the star or neutral point of the primary is earthed, the third harmonic present in the alternator voltage may appear on the secondary side. This causes distortion in the secondary phase voltages. Due to these disadvantages, this connection is used very rare in practice. Then we will move on to star delta connection. In this type of connection, the primary is connected in star while the secondary is connected in delta as shown in figure 4.5. So, the primary side is connected in star, whereas the secondary side is connected in delta. The same type of connection can be represented in another way. So, this is star where one end of all the phases are interconnected, whereas here you can see A phase, the other end of A phase is connected to the starting point of B phase. The second that is the other end of B phase is connected to the starting point of C phase, and the other end of C phase is connected to the starting point of A phase. So, this is star where the other ends of each phase are connected to a single point, whereas here they are interconnected with each other. So, this is star, primary side is star, the secondary side is delta. This type of connection is commonly employed at the substation end of the transmission line. The main use of this connection is to step down the voltage. The neutral available on the primary side is grounded. It can be seen that there is a phase difference of 30 degrees between the primary and the line voltages. This connection suffers no problems due to the unbalanced load, as the secondaries are connected in delta. These type of transformers are commonly employed at the receiving end. So, here are the few advantages of star delta connection. One is the primary side is star connected, hence fewer number of turns are required. This makes the connection more economical for large high voltage step down power transformers. The neutral available on the primary can be earthed to avoid distortion. Number 3, large unbalanced loads can be handled satisfactorily, and here is the disadvantage of this star delta connection. In this type of connection, the secondary voltage is not in phase with the primary, hence it is not possible to operate this connection in parallel with star star or delta delta connected transformers. Then delta star connection. In this type of connection, the primary is connected in delta fashion while the secondary is connected in star fashion as shown in the figure. So, this is the primary side where it is delta connected, and here is the secondary side connected in star, just opposite to that of the previous one. Before concluding this session on transformers, we will have a quick recap of whatever we have learnt in this session. So, we have done few problems on the transformers, and we have dealt with 3-phase transformers and various connections associated with the 3-phase transformer like star star, star delta and delta star, etc. Thank you.